Alright, so this will be our first lecture on the material for the final exam. And we're going to study optics, which is the study of light. One of the things that folks discovered in the middle of the 1800s is that you can combine all the various laws of electricity and magnetism into four called Maxwell's equations. We talked about how we had to modify Ampere's law to make that happen, and these are the four in what we call integral form Maxwell's equations, which describe all electromagnetic theory. It is the single most successful theory that anybody's ever come up with. If there's ever any doubt about its results, then, for example, Einstein, looking at electromagnetic radiation and regular mechanics, realized there was a contradiction, and so he decided these must be right, and that leads to special relativity, general relativity. So, one of the things that these lead to, that Maxwell figured out, is you can combine them and get to a wave equation, just like what we had for waves in a string. And not only that, but it predicts what, in that case, it predicts what the speed of light should be. It ought to be 1 over that square root of mu naught epsilon naught, permittivity and permeability of free space. You plug those in and you get a number, which people were then able to go out and measure and verify that the waves actually do follow that, have that particular speed. So the late 1800s was the verification of the fact that light is an electromagnetic wave. Hertz, who the unit's named after, basically built what we would now basically call a radio or a transmitter. He was able to take one coil and generate a spark and have it cause a spark in another coil. And that was sort of the first verification that these electromagnetic, and he was able to estimate what the speed was. Didn't understand it was light quite yet. People had measured the light independently. One of the ones that you can read about in the book is an old estimate people used by looking at the revolution of one of the moons of Jupiter, and they were able to place a limit on it. Actually comes out. And then later, Huygens made another estimate. Huygens believed light was a wave. Then there became a mechanical experiment. We actually did this one in a sort of a junior, senior level optics lab, in which you spin a gear really fast, shine a laser through it, and do some synchronize, and reflect it back over a long distance and synchronize, and you can get the distance. If that distance is long enough, you can get a big enough delay that you can figure out what the speed of light is. So people were measuring it independently and verifying that the electromagnetic waves do have the same speed as the speed of light. That wave we visualize as a transverse wave. Question is, what's the medium? Well, the medium is just the electric and magnetic fields. But what we learned in Faraday's law is that, in Lorentz force equation, is that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. So that last slide would be if you could see the fields, they would look like that. If you see one coming at you, then it would oscillate like those. I do believe we've got a canvas link, because I think I've got that up. Let's go take a look at that, and you'll have access to that too. Well, here it is. Let's get here. There it goes. And you can kind of let it run. You see it going by, and the electromagnetic fields oscillate, and they're perpendicular to each other. And they're both perpendicular to the direction of the velocity, so the direction of the travel, so that's why we call it a transverse wave. We think of the path of everybody's seen a laser beam, so a laser beam kind of gives you the path of what we call a ray, a light ray. Then we have perpendicular to that what we call the wave fronts. That would be regions where we're at the peak. So, that peak right there, moving peak, would be a wave front, would outline a wave front. Plane waves, as we call them, have planar wavefronts. And of course, the speed is going to be, we had what? Frequency times wavelength, which you can rewrite in terms of omega and k. And so the speed of light, that number we just showed, is about 3 times 10 to the 8th meters per second, is f times lambda. There's all the possible electromagnetic radiation spectrum. Here's over the wavelength, here's over the frequency, and since their product is the speed of light, then if you know one, you can get the other. The visible thing that we normally think of as light is only a small part of that. You can see that we've got, in this case, shorter wavelength, which is ultraviolet, X-ray, and gamma. Our eyes don't respond to those. We've got longer wavelength, infrared, microwave, things we use for AM and FM TV, satellite signals, cell phone signals, all of that good stuff. The visible part is only a small part. Now, other animals can see a different spectrum than we can. Some can see up into the ultraviolet, some can see down into the infrared. We're going to now use light to indicate any of those particulars. Notice that AM radio waves are about 1 kilometer long, down to gamma rays where like a picometer to the minus 12, and that corresponds to frequencies on the order of 10 to the 5th hertz up to 10 to the 21st, 22nd hertz. Big range. And you can look over these notes, there's some definitions of what radio waves, microwaves, infrared waves. Visible light runs from about 4 to 7, 10 to the minus 7. Those are typically measured in what are called nanometers, which is on the 10 to the minus 9, or angstroms, 4,000 angstroms or 400 nanometers. Nanometers 10 to the minus 9. So visible light runs from the purple, which is about 400, to red, about 700 nanometers. Then ultraviolet, X-rays, gamma rays. There's some pictures of the Crab Nebula in each of these different wavelengths. X-rays, clockwise from upper left. So upper left would be here, that's X-ray, visible, infrared, well, clockwise, so I guess that's infrared. That's radio, and that's infrared. Astronomers use all the different parts of the spectrum. All right, that's the end of the first section. The problems are going to be basically calculating wavelengths and frequencies from C equals lambda times F. We'll see you in the next video.